Up next, part two, as we, I think, increase in stellar mass. Robbie Wilson's going to talk about TRExS, updating yields and science opportunities for this program. You have
And then the laser is here on top. Just press and hold it.
Okay. Hey everyone. So I think I was kind of putting together this talk. The idea I had, which may or may not be good, is to sort of grab a handful of ideas and just throw them at the wall and see like what people may or may not be interested in. So it'll be a very brief dive across a couple different things that hopefully are interesting to people in here. Yeah, so Roman's going to be an exquisite transiting planet mission, which was not quite intended, but it's going to have a lot of good opportunities. And so first I wanted to just introduce our collaboration, which is Transits, the Roman Galactic Exoplanet Survey, or TRExS. And we recently got funding for cycle 1, and we have sort of three specific goals. So one is to produce a catalog of transiting planet candidates by searching all 100 million stars or so that we expect. We're preparing for 100 million. Real numbers probably closer to 50 million or so. And then in order to do this, we need stellar parameters. So we have a group. Our team is also putting together stellar parameters for every star in the Galactic Bulge Survey. And we're putting together a supplementary catalog of candidates with eclipse measurements, which we should be able to get from GPTS also. I think Avi's going to talk a little more about that after me. And then at the sort of end of season 3, once we are starting to get the data a little better understood, we'll do a more comprehensive completeness reliability analysis. So all of the occurrence rate, all of that occurrence rate analysis that Phil talked about on the previous slide will be accessible to everyone in the field. That's these are sort of the main goals of our team. This is just a pipeline, so I can convince people we know what we're doing. I'm not going to talk about it. You're welcome. And we're just going to go straight into sort of 3 really big science goals. There are 3 big science unique opportunities that Roman will provide that other surveys haven't yet. And so showed on the right is the yield of planets broken down on this axis here by the size of the planet. So here's all the small planets here. And then the y-axis is broken down by spectral type. So you can see what kind of stars they're all being found around. And just I'll keep coming back to this slide over and over. The first thing I wanted to talk about was some demographics of ultra-hot Jupiters. And I won't go into this in detail, other than to say we have UHI. Johns Hopkins has been simulating this. And there's sort of 2 ways we can study hot Jupiters in the survey. So one is through the multi-band photometry, being shown on the left. And so if you have a very clear atmosphere, as you see, there's going to be slight differences in the inferred radius between planets. And then through eclipses, where you can look at an emission spectrum and see, you can potentially see differences from filter to filter and get temperatures. And so, they've done this really great simulation. And here's one of the results. Here we can distinguish here's an example planet of there we go, inflated Neptune mass planet that's about a half a day period, 3,000 Kelvin, and we can actually distinguish the secondary eclipse to about 10 parts per million. And if you repeat this for a whole yield of planets, we should expect about 500 chromatic transits total, and then of order 1,000 eclipses from planets. And there's a ton of science we can do with it that I'll let Avi talk about. So one of the next opportunity is demographics for really rare systems, and this is just sort of a catch-all for a bunch of stuff that I'm going to go through really quickly. So first one is giant planets, right? These are sort of intrinsically rare, sort of 1 in 100, 1 in 200. And Roman will find them in spades because they're observing so many stars. So one of the potential results we could find is up to 10 planets with detectable orbital decay, and maybe about 1, which 1 doesn't sound like a lot, but if we can confirm that, that will double the number of known planets with detected orbital decay. and 10 would be 10 times more. We only have one right now. This is some great work led by Kylie Carden at Hopkins. So other rare planetary systems, M-Dors with giant planets. So we're predicting sort of order several hundred, up to 1,000. There's currently about 30 that are known. And this is a particularly interesting group of planets because, one, they shouldn't really exist based on how efficient formation has to be for them to be created. And then the detections themselves should be relatively reliable compared to some of the other false positives, or some of the other planet types that will have a high false positive rate. So there'll be high signal to noise detections. So we should be able to exploit color information. And we should be able to see secondary eclipses. So we should be able to see secondary eclipses. Or if we don't see an eclipse, it's certainly not a star. So it's really hard to reproduce these shapes. Okay, so that's another one. Another one that we're really interested in is the small planets around M-Dors. We've heard a little bit about this, but I'm especially interested in habitable zone planets. And this is a case where we're predicting now with these new yield estimates of order 20 to 30 from the whole survey. And so this number's increased since the last design, which offered higher cadence observations, which is allowing us to push down to smaller planets. So since the ROTAC has changed the survey, I think we actually are going to do a little bit better for some of these smaller low signal to noise planets. And on the right is showing sort of where they're coming from. So this is sort of the state of the art at the bottom of a total number of M-Dwarfs that have been searched for habitable zone planets. Romans at the top, sort of order 50 to 100,000 low mass stars should be searched and reasonably effectively. And the second part of this is these stars should be much more amenable to follow-up than most of the stars in the sample. So the predicted parallaxes are pretty large, and so I think potentially we could get parallaxes as early as year 2 for some of these systems. Jessica nodded, which is great. So, so hopefully by the end of the first 2 years of the galactic bulge season, we should have of order 15 to 20 habitable zone candidates with radii less than 1.5 Earth radii. So we've been preparing for this by looking at, so one of the issues is this could be overestimated due to flares and activity from these stars. So we've started preparing for this by simulating noisy light curves. So we took some test light curves, then resampled them to the Roman cadence. Presumably these should be worse because flares are brighter in the optical, I think. Yeah, okay, good. And I think, so we've taken these light curves, we've added some noise to them to be a little bit more Roman-like because TESS has a higher precision than what we'll see with Roman. So that's being shown here in these plots. And so these are scaled to be at the same signal to noise, but with different amounts of white noise added. And the red line is sort of the boundary between the sub-Neptunes and rocky planets, sub-Neptunes and super-Earths. And what we're seeing is there's not a significant change in the recovery fraction with signal to noise, telling us our pipeline's doing a pretty good job, taking out flares, and it's not significantly impacted. So we think we're doing good there. So we should be, this is a good opportunity. Okay, and the last real big opportunity here is demographics of planets across all major galactic populations. So exactly how we're going to do this, we'll get to in a minute, but Roman has a pretty incredible depth. So here's the galaxy in pink, are all of the currently known planets. And you can see like a few outcroppings. So this one right here is from Kepler. The big sort of blob all around the center is radial velocity and TESS detections. There's a couple small outcroppings from K2. These are microlensing detections. And if we add the simulated Roman detections on top, we get this. And so we should really be blasting all the way across the Milky Way with these planets. So in terms of where exactly we're finding these, so based on simulations, we should find about 2/3 to 70% in the bulge in the bar, which is a pretty completely unexplored parameter space, and about 30+% in the foreground disk, both the thin and thick disk. This is assuming constant occurrence across the Milky Way, which we think is probably not true. And so stars are correlated with metallicity. There's a bunch of studies that say that. And if you account for that, then all of a sudden the fraction of planets we find in the thick disk and the thick bulge is down to about 3%, and these numbers change pretty drastically. And so one of the questions is, how are we actually going to be able to make this measurement? And I think the answer is forward modeling with galactic models. And if you want to hear more about that, talk to Matt. He's over there. He's over there. There you go. He has a poster, and he's been thinking about this for a while now. Okay. All right, so the last opportunity now I'll talk about is a mix of this galactic model idea, and really long period planets, because we're observing so many stars, we have to really overcome the geometric transit bias. Start to push down, so here's sort of the anticipated yield. If you go out to 10 days, about half of it drops off, so median planet should be a period of about 10 days. If you go out to 100 days, you still have about 10,000 left. At a year, you have about 3,000. 3 years, you have about 700, and then of order 100 planets beyond 10-day orbital periods. So these last ones are going to be like your true Jupiter analogs. And that is quite consistent with the sensitivity from microlensing. So you have this really great opportunity to combine the transit sample with the microlensing sample. And again, I think probably the way to do this is through forward modeling, and it's going to be a result we'll learn how to do. But if we get this right, we have coverage from 0 to infinity of giant planets at the shortest periods, out to free-floating planets with no separation whatsoever. And that's sort of the summary things to look forward to. Last thing I wanted to say is this last point. A year from now, we will be finished collecting data for season 1, and we'll be knee-deep in validation reports. So we're looking forward to it. Thanks.
That's great. Thanks, Robbie. So questions for Robbie? I don't see anything yet. Okay, I'll let people think for a minute and I'll ask you a question. What do you think we're going to learn from the transiting planets in the galactic center field?
Yeah, so the galactic center field is going to be a lot tougher. I think the extinction hits you really hard. So I don't think we're not going to reach the center directly unless we get lucky with like a subgiant or some really luminous star. And I think we're probably going to be limited to like 5-6 kiloparsecs maybe to the disk stars.
Jessica.
Do you have halo stars in your sample? I was curious.
Yeah, we do, and we had a few halo detections, but they were like of order like 1 in 10,000. So potentially we might have like 10, which would be really cool.
Question at the back.
I was going to ask a similar question, and how many of the exoplanet detections are you going to get on the other side of the bulge? We're able to get?
Yeah, so detections on the other side of the bulge, quite a bit, like of order 5 to 10,000, I think. So you can see this plot, the one with Matt's face on it. I think I went too far. Nope, too far again. There it is. Yeah, so basically what's being shown here is the rotation curve of the galaxy. So one of these peaks is the near side of the bulge, one of these peaks is the far side of the bulge. So we should be able to cover it pretty well, actually.
That's pretty cool. All right, well, thank Robbie again. Excellent. you.